Hey, so for Module 5, for this Advanced Concepts presentation, the topic of discussion is cellular respiration. So just a brief overview to start. Cellular respiration is the process in which cells derive energy from glucose. So we're going to take one glucose molecule in this presentation, and we are going to generate just a little bit over 30 ATP through this process that we walk through. So the process includes 4 steps: glycolysis, pyruvate oxidation, the citric acid or Krebs cycle, oxidative phosphorylation, which includes the electron transport chain and ATP synthase. All right, so glycolysis. So early on, we are going to take glucose and hexokinase. That enzyme is going to break that down into glucose 6-phosphate. Now, early on, we're going to lose an ATP right off the bat. We're going to utilize an ATP for this process to happen. As we go throughout glycolysis, throughout this chain, and breaking down our glucose, fructose 6-phosphate is also going to use an ATP to get to fructose 1,6-biphosphate. Now, as that's broken down, it gets broken down into 2 parts here. So we get the dihydroxyacetone phosphate and our glyceraldehyde 3-phosphate. Now, with this, what we're going to see is that going into step 6, the glyceraldehyde 3-phosphate will stick around in this glycolysis cycle, but the hydroxyacetone phosphate will not. So, as this breakdown occurs, we will get 2 molecules of this glyceraldehyde 3-phosphate that will kind of carry us through the rest of this glycolysis cycle. So, as we go from glyceraldehyde 3-phosphate to 1,3-biphosphoglyceraldehyde, we will gain a couple NADH molecules here. And then as we continue through this cycle, we get to 3-phosphoglycerate. We pick up an ATP from this reaction here. Again, moving along that chain, we go from PEP to pyruvate, and ultimately closing up this cycle, we'll add 1 more ATP molecule here. So, just in review and summarizing those steps, steps 6 through 10 are going to occur twice because step 5 does leave us, like I mentioned, with the 2 glyceraldehyde 3-phosphate molecules. So, in total, we are going to net 7 ATP. Reason why is we produced 2 ATP. We have the 2 NADH that we picked up, and in that conversion, one NADH is equivalent to 2.5 ATP. So ultimately, we gained 5 ATP there, and then we did utilize, and 2 ATP were consumed in those beginning steps of glycolysis, steps 1 through 3. So pyruvate oxidation. So we're going to take that pyruvate, and this is where we're going to get the acetyl-CoA that will ultimately kick off that Krebs cycle for us. And in the process of this, we will pick up 2 more NADH molecules, which again, as we convert that, we will gain 5 ATP here, and we will also get the 2 acetyl-CoA molecules that are going to drive us into the Krebs cycle here. So, as we move into the Krebs cycle, again, like we talk about, the pyruvate oxidation creates that acetyl-CoA for us that drops us into this Krebs cycle that we see here. And so this is where we're going to gain a lot of ATP molecules as we go throughout this chain. And so we'll sort of work around the circle here. So early on, as we go from citrate to isocitrate, that isocitrate to alpha-ketoglutarate process from this isocitrate dehydrogenase takes us from the NAD+ to NADH, so we pick up another NADH in that process there. Moving on here, we get another NADH picked up from alpha-ketoglutarate to succinyl-CoA. All right. And then, as we move through succinyl-CoA to succinate, that GTP, we have a GTP that's picked up in the process. So this GTP is, for all intents and purposes, we're going to treat it as an equal to ATP. GTP and ATP are similar. It's just more so where in the body they're utilized. So GTP would be used in something like the liver, whereas the heart would utilize something like ATP. But for all intents and purposes, we'll keep, from a counting standpoint, they're the same. Continuing the Krebs cycle, so going from succinate to fumarate, we pick up a couple FADH2 molecules here. And then moving through the cycle, malate to oxaloacetate, we gain a couple more NADH molecules. And then during this process, oxaloacetate will regenerate itself and continue through this Krebs cycle once again. And so, given that we had 2 acetyl-CoA molecules from pyruvate oxidation, we'll run through this twice, so it'll double all the numbers that we just talked about here. So from a production standpoint, we gain 6 NADH, which is equivalent to 15 ATP. The 2 FADH2s that we picked up is equal to 3 ATP, and then we did gain 2 ATP or GTP in the process, totaling us out at 20 total ATP during the Krebs cycle. All right, so moving through this process, and as we look at oxidative phosphorylation, so this takes place in the inner membrane of the mitochondria, and so a couple of those NADH and FADH2 molecules that we pick up during the Krebs cycle are going to share their electrons here. All right, so there are our electron carriers, and they're gonna help us through this process. So, they're gonna share their protons. They serve as electron carriers once they leave this oxidative phosphorylation process, but they're sharing their protons to help us with our proton gradient. All right, and we can see that here, that NADH loses that proton to help us with that proton gradient, and ultimately what's going to drive this electron transport chain. Okay, so all right, so as we work through this, we will ultimately, this will serve a couple purposes for us. So the NADH will turn back into NADH plus and work itself back into the Krebs cycle. Same thing with FADH2 and FAD. All right, and then as we give those protons to this proton gradient and work through the electron transport chain, those protons serve a very important purpose as we look into this last step here. All right, and that is going to be our ATP synthase. So a couple of the functions here that we want to look at just of the electron transport chain, and the reason it's important is we are going to, as I talked about, regenerate those electron carriers. All right, so NAD plus and FAD will work their way back into the Krebs cycle, and then again we're going to create that proton gradient here. All right, so when it comes to ATP synthase, all right, we have two things that we look at here in terms of ATP synthase. All right, so the F0 portion is just describing the proton channel. So this is within the membrane, and this is where our protons are coming through the channel to work into F1. Okay, and F1 is the catalytic component. It's where the ATP is generating and being released into the cytoplasm. So we have the rotor, the headpiece, and the channel. That rotor is going to rotate as protons enter and exit. The headpiece is where the ATP synthesis is actually occurring, and then the channel is, again, where those proteins are entering and exiting. Okay, so all in all, as we just to quick summarize this process, we are going to gain 3 more ATP for every 9 protons that come through this ATP synthase process, and ultimately it'll increase our net count. So net totals, we talked about the conversions earlier. So glycolysis will net us 2 ATP, and those 2 NADH does net us 5 ATP. However, we have to understand that we are going to lose a couple of ATP because that NADH that's produced is produced in the cytosol, and it does not, that NADH is not able to work itself into the membrane because that membrane is impermeable to NAD. So it can't work itself into the mitochondria on its own. It needs that shuttle system to get them in there, and ultimately that's going to require energy. So we will produce something like 3 to 5 ATP here. So for this case, we're going to presume that we'll lose a couple ATP due to this shuttle system, and that'll knock our count down. Pyruvate oxidation, we gained a total of 5 ATP. Krebs cycle, as we talked about, we gained 2 ATP, 6 NADH converts us to that 15 ATP number. The 2FADH2 gets us 3 ATP, and then during oxidative phosphorylation and ATP synthase, we gain 3 more, netting our total at 33. Thank you.